Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 13, Periodic Motion, Video 2. Today's topic is simple harmonic motion, Part 1. The objectives are: note condition of simple harmonic motion. Note acceleration is not constant in simple harmonic motion. Note the equations of simple harmonic motion. Understand SHM is the projection of a uniform circular motion onto a diameter. Be able to do calculations of simple harmonic motion. Simple harmonic motion is a special case of oscillation when the restoring force Fx is directly proportional to the displacement from equilibrium x, such as Fx equals negative kx. The oscillation is called a simple harmonic motion, or SHM. When that happens, Ax equals negative k over mx. So whenever either case occurs, you should know the motion is simple harmonic motion. For example, Ax may be equals to negative 3.5x. Right away, you should know this motion is simple harmonic motion because it satisfies these conditions. Ax is directly proportional to negative x. This negative sign means the acceleration and the displacement always have opposite sign. This acceleration is not constant, so we can't use the constant acceleration equations. Here is the diagram of Fx versus x. In ideal case, the restoring force obeys Hooke's law. Fx equals negative kx, so the graph Fx versus x is a straight line. But in typical real case, the restoring force deviates from Hooke's law. But Fx equals negative kx can be a good approximation to the force if the displacement x is sufficiently small. Simple harmonic motion is a projection of a uniform circular motion onto a diameter. Here we are showing a red ball that moves on a uniform circular motion. Its shadow, the blue ball, actually moves back and forth on the x-axis in simple harmonic motion. Here is another animation showing how the two corresponding to each other. Displacement, speed, and acceleration of simple harmonic motion. So basically, we know the object moving a uniform circle pretty well. We just have to find its shadow. So this diagram shows a ball moving a uniform circular motion. The shadow moves back and forth on the x-axis in simple harmonic motion. To find x, we can use trig, SOHCAHTOA, x equals a cosine theta. Cosine because it's adjacent. By the way, this circle is called a reference circle, and OQ is called a phasor. So from the reference circle, we can also find Vx. Vx equals a negative VQ sine theta because V is pointing in the negative direction. Similarly, we can find Ax equals a negative AQ cosine theta. It's cosine because it's adjacent to theta, and it's negative because it's opposite, going to the left. Since Ax, we know Ax equals to centripetal acceleration equals V squared over R. In this case, R is A. So AQ equals omega squared times A. We substitute AQ into Ax, so we have Ax equals negative omega squared times A times cosine theta. A cosine theta, this gives us x, so Ax equals negative omega squared times x. We also know from Ax equals to net force over m, so Ax equals negative k over m times x. That means omega squared has to be equals to k over m. So omega equals to square root of k over m. So these are the three equations for displacement, velocity, and acceleration. From here, we also found angular frequency or angular speed. So first, these are the three equations. Omega equals to square root of k over m. So omega represents angular speed on the circle, angular frequency for simple harmonic motion. Basically, they are the same thing. This equation tells us that value omega is not yours to choose. It is predetermined by the values of k. That's the spring constant. Its unit can be represented as newtons per meter or kilograms over second squared. And the mass m, the unit for omega, is radians per second. From here, we can figure out frequency. Frequency equals omega divided by 2 pi, and t equals to 2 pi divided by omega. So this equation shows a larger mass, which with its larger inertia, will have less acceleration, moves more slowly, and takes longer time for a complete cycle. So the bigger the m, the bigger the t. On the other hand, a stiffer spring means one with larger spring constant k exert a greater force because F equals to kx at a given x, causing greater acceleration. With greater acceleration, the object will have higher speeds and a shorter period. Don't confuse frequency and angular frequency. Frequency tells you how many cycles of oscillation occur per second. Well, angular frequency tells you how many radians per second this corresponds to on the reference circle. So period and amplitude in simple harmonic motion. So omega equals to square root of k over m, and here's F equals 1 over 2 pi times k over m, and t equals to 2 pi times square root of m over k. So the period and frequency are completely determined by the mass and the force constant k. Period and frequency do not depend on amplitude A. The bigger the amplitude means the body reaches higher value of x and is subjected to larger restoring force. Again, this larger restoring force corresponding to a greater speed. So this exactly compensates for having to travel larger distance. So the time is the same. You have larger distance when you have larger speed. So time remains the same. That's why period does not depend on the amplitude. Let's look at this example. A spring is mounted horizontally with its left end held stationary. By attaching a spring balance to the free end and pulling toward the right, we determine that stretching force is proportional to the displacement, and that a force of 6 newtons causes a displacement of 0.3 meters. We remove the spring balance and attach a 0.5 kilogram glider to the end. Pull it a distance of 0.02 meters along the frictionless air track. Release it and watch it oscillate. First, find the force constant of the spring. Then find angular frequency, and the period. So force constant, let's see, we already know the spring force and we know the displacement. So from there, we can find force constant is negative Fx over x. The force constant is 200 newtons per meter or 200 kilograms over second squared. Next one, find angular frequency and the period of oscillation. We know angular frequency, omega equals the square root of k over m. Plug everything in, we figured omega equals to 20 radians per second. Frequency equals omega over 2 pi. So that gives you 3.2 hertz. The last value is period. Period is 1 over frequency. That gives us 0.31 seconds. So in here, you need to know, even though the amplitude is different, but it doesn't make any difference on the force constant or frequency or period. We didn't need to use the amplitude to find omega f and t because this quantities does not depend on amplitude. That's it for this lesson. See you next time.